That's not how it's supposed to work. All right, so welcome back, everyone. So it's the last lecture of the semester. So the weather says it's time to kind of, start to change. So seasons and what we're doing. Yeah. So this this lecture is going to be trying to be a review of all the material in the course. My main objective will be to kind of walk through the entire practice. So final, and I'll probably stop and kind of focus on a few things that I think I think it does a fairly good job of like reviewing everything in the course. And I'll probably try and stop and throw in a few other things beyond so what's on there. But also, if you're here or online, feel free to kind of stop and ask me questions about anything else. You can do that at the beginning or when that topic is comes up in the review. So very quickly, we're at the very end of the semester. Homework 5 is due tomorrow. I have my office hours tomorrow morning, and we'll try and be available on Zoom or on Canvas, so to answer questions. But that is due tomorrow at the end of the day. And then the final is going to be a week from tomorrow. So at this end of the finals period, again, I think it's available from 8 p.m. Thursday till 5 p.m. on Friday, but you'll have 2 hours once you start. So you can start anytime. During the scheduled final exam time, Friday, 10:30 a.m. to 12 p.m., I will be here in this room. You're welcome to come here in this room. I'll also be on Zoom. And so if you're taking it during that time, I can help answer questions on it. I'll try and be available on Canvas, but I probably won't be up all night, for instance, or other ways in case there are questions. Hopefully everything will be clear. But so because I will be more available during this time, I recommend you come and take it during that time in case there are questions. So great. So good. So let's get on with it. So, a couple of other things. If you are a graduating computer science, computer engineering, or data science major this semester, I guess there's an exit survey I'm supposed to tell you to take, and there's a class evaluation form. Go and fill out that evaluation form about the course and the instructor, me. I hope you give me good scores, but I'd like your honest feedback about everything. I always like to improve stuff every time I get a chance to teach it. So if you have feedback, please leave it. That'd be great. Okay, before we first, are there any kind of general questions, or otherwise I've got somewhat of a plan to go through. So great. So I kind of want to overview and some big picture things from the class before we get into the final exam, the practice final. The first one is the input to the algorithms we covered in kind of the second half or second 2/3 of the semester was either of the form XY or just X, right? And the difference here was that the XY, these were so supervised, and there was this response variable Y that we were trying to predict, where this was supervised. Okay, and then we weren't trying to. So for this one, we're trying to predict. In this one, we're trying to basically find some structure in the data. And so if we thought of it on these axes, they're kind of 4 boxes of things that we that we covered. Okay, there was the let's see, the classification. Okay, was in this box, and this is where you have kind of a, or blue is usually minus points, and there were, so these plus points, and you were trying to build a function that would predict if a new point was going to be a plus or minus function. But we also looked, and this was earlier in the semester, we looked at these regression. Okay, and this here we thought of the data on our RD, and the y variables was also in the real numbers, and basically there was a function we're trying to predict from x to the real values, and this was trying to predict these y values. So if we think of the output here, it can either be a minus or plus, or more generally a class. It could be a discrete set, or it could be the real values, something like R or more generally RK. And so if we're trying to predict real values, we got something like regression. We're trying to predict a class of plus or minus, or more generally it's a classification. And the unsupervised setting, we could think of this as, so clustering. Here we just have data points, they don't have labels, and we kind of group them, and they end up being these outputs in classes 1, 2, or 3, but we didn't know those ahead of time. We're trying to kind of just find that structure. And we also had this situation where we're in this dimensionality reduction, where we're in this very kind of high dimensional space, and we got this idea of finding this kind of low dimensional space where we can project all of this data onto the space, right? So if we have V1 and V2, then we can project a data point X onto a projection onto a subspace equals, say, V1X is the first coordinate, and say V2X would be the second coordinate. And so we would get this new representation in this space, and this through this dimensional reduction. Okay, and this is kind of an overview of these class of techniques. You know, data analysis is a bit broader, it deals with other data types, but a big, huge chunk of it, and what we covered in this class, was dealing with these kind of, the input is these kind of vector valued sort of quantities. One really more important point is that with this prediction-based thing, we can do cross validation, where we will hold out part of the data and don't use that to build the model, and use that held out part, the test data, to evaluate how well the model works, or to tune the parameters. Okay, and that was something that we can do in the supervised setting, but not the unsupervised setting. There we have to rely on some underlying modeling, and we just looked at simple sum of squares modeling in this course, but that can, the next courses you might take would go beyond that. Similar, we looked at mostly sum of squares sort of problems in these settings, but again, the cross-validation is how you would want to evaluate that, not just what the cost function told you. All right, so that's kind of a big picture of kind of the data analysis from the perspective of this course. I want to just start with that. Okay, so let's get into the exam, and we're going to kind of just go through it in order here. And all right, so I've got all the questions, so I think we should go through them pretty quick. The first one is a probability table. We have two random variables, or two, X and Y. and we want to know the probability of x equals 1, and this is in a table. And so for this, we would add up, this would be 0.1 plus 0.3, kind of everything in this table should give you a 0.4. Okay, x equals 2, intersect y equals 1, right? So that means both of those are true. That means it's just this entry in the table, 0.05. That's the joint probability, they're both true. X equals 3 given y equals 2, right? So now we are restricting to y equals 2. We're only looking up at this setting. We want to know the probability that x equals 3 given this is true. So it's a little bit trickier. It's 0.2 divided we only consider the probability in the second row. So the total of these adds up to 0.3 plus 0.25 plus 0.2, right? And this gives us, that's going to be 0.72 over 0.75. Okay, that's enough to simplify. You don't need to simplify beyond that. Okay, right? So that would be the probability of this conditional probability. The condition restricts us to a row. Okay, what is the marginal distribution for x? The marginal distribution for x is going to be the probabilities of just x, and we're going to marginalize over y. We're going to ignore the component of y. So we're just going to write these up here, 0.4. I'm just adding everything up in the column, 0.3 and 0.3, right? So it would look like a table, x equals 1, x equals 2, x equals 3. And this would be 0.4, 0.3, 0.3. Okay, what is the conditional probability that for y given that x equals 2? Right, this is basically the same sort of question as we had in part C. But we want to write out the probability table now. So this is now going to correspond, conditional probability for y given x equals 2. It's going to be this part of the table here. And we have to write out, given that it's 2, we're dividing those quantities by, so y equals 1 or y equals 2. And there are two quantities in this table, 0.05 divided by 0.3 and 0.025, no, just 0.25 divided by 0.3. So now this is as a table. This gives me the conditional probability table for when x equals 2. So I guess that would be 1/6 and 5/6. Okay. Are random variables x and y independent? Okay, so we can say that the answer to this one is going to be no. That would have to be that if I conditioned at any kind of at any value of x or y, that it would not change the conditional probability from the marginal probability, right? That'd be one way of saying it. If I looked at the total probability of x equals 3 and the total probability of x equals 2, then the joint probability would have to be equal to those, right? So we can check. Let's check this element right here. Okay, so the total probability that y equals the probability that y equals 2, remember, is going to be equal to 0.75. The probability that x equals 3 equals 0.3, and the probability that x equals 3 and y equals 2, this is just in the table, 0.2. If they were independent, it would be the product. This is not equal to 0.3 times 0.075. Those are not equal to each other, so it's not independent. There are a variety of ways you can check. Okay, however, is x equals 1 independent of y equals 1? Okay, the probability x equals 1 independent of that. And So let's see. So the probability that x equals 1 is 0.4, right? We established already that the probability that x equals 1 is going to be 0.4 overall. If y is equal to 1, conditioned on that, so the total, the marginal probability here is going to be 0.25. So I want to check out the probability that x equals 1, given that y equals 1. This is going to be equal to 0.1 divided by 0.25. And the answer to this is going to be 2/5, which is 0.4. So these are the same. So the probability that x equals 1 is 0.4 is independent of if y is equal to 1. Well, it's still going to be 0.4 probability if I did this right. So these are going to be independent of each other. Okay, so events can be independent. These are events independent, even though the random variables are not independent. Okay, great. Probability review. Let's look at, this one is about Bayes' rule. Remember, Bayes' rule, Bayes with an S was a person, so the apostrophe is afterwards, and this is the probability that the of the model given the data is equal to the probability of the data given the model times the probability of the model divided by the probability of the data here, right? But we often can just say that this is proportional to the probability of the data given the model times the probability of the model, because without this denominator, because that will be the same for everything. And so that's just, so there's some constant factor in front here. Okay, so now we have prior knowledge that there are two models, M1 and M2, and we want to compare these. And so we have probability that M1 given the data is proportional to probability of the data given M1 times the probability of M1, and this is equal to 0.5 times 0.25. If I do the same thing for probability of M2 given the data, this is going to be proportional to, with the same scaling factor, this will be 0.01 times 0.75. This one is going to be 0.125, and this one is 0.075. And so this one, model 1, has a higher probability of being the right model. Okay, I can compare these now because they're both, there's implicitly, I'm dividing through by the probability of the data, which is a constant, right? So I'm able to compare these concepts because I factor the constant out. Okay? Good? Okay. Question 3. I observed 3 data points, x1, x2, x3, drawn IID, identically and independently distributed from an unknown distribution. Given a model, can I calculate the likelihood that each data point as 0.5, 0.1, and 0.2 was the likelihood of seeing all these data points given the model? Okay. So the probability of x1, x2, and x3 of all of them given the model when I know them individually, well, because I know this implies that they are independent, and I know that this is then equal to the probability of x1 given the model times the probability of x2 given the model times the probability of x3 given the model, right? This is a key assumption. This independence allows us to decompose the probability of seeing all of them as the product of them. We typically worked at this through a log transform where it's a sum, but if you're looking at the probability or the likelihood, well, then it's going to be a product. And so I can just set this equals to 0.5 times 0.1 times 0.2. And what is this going to be? 0.001. Something like that. Yeah, so that's the joint probability. These get pretty small. One of computational reasons we use the log transform is when you start taking a product of 10 or 100 or 1,000 of these things, they get to really small precision, and that's hard to deal with numerically, whereas the log transform, the sum, is easier to keep track of. Okay, great. It's pretty straightforward. Okay, concentration of measure questions. Given a PDF F, so we have a random variable X drawn from this PDF. The expected value is 3 and the variance is 10, right? So now we consider 10 IID random variables, and we'd like to consider this average of them, okay? So by the central limit theorem, we know that the first two facts that the average is the same. Equals 3, right? So the expected value of the average of the independent ones is the same as each of the individual ones. And so this is 3. The variance is equal to the variance of each individual one divided by n. Right? So now we're going to get 10 divided by 10, which is equal to 1. Okay? The standard deviation goes down by square root n, right? But the variance goes down by n. Okay, what is the standard deviation of x bar? Well, it's just the square root of 1 is 1. Okay? Standard deviation, remember the standard deviation is the square root of the variance. Okay? And, okay, now here are the fun questions. Which is larger? Which is larger, probability of x greater than 4 or probability of x bar greater than 4? I like this question. This is a fun one. Here's what you should do. You should draw a picture of some distribution. And all we kind of know is that the distribution has a mean of 3. This is like the PDF of F. Okay, and we're interested in identifying for, say, 4, kind of the probability that x is greater than 4 is this filled in area here. This is the probability that x is greater than 4. Okay? And I want to compare that with the same thing for x bar. What do we know about x bar compared to x? Well, you know, its variance is smaller. And so generally what that means is that it's going to be a narrower distribution. It's going to look something like this. It's going to be more narrow here. Let me, well, it's a little bit more exciting, more narrow. Okay? And so now if we want to look at for x equals 4, what is the area under the curve here? Area greater than 4. This now corresponds with the probability that x bar is greater than 4. Which one is bigger? Which area, shaded region, is larger here? Yeah, it's the one for x. X is bigger because this is a greater than the mean, and I preserved the mean, and I've just kind of squeezed it, and that's going to squeeze some of the stuff past 4 to be less than 4, basically is what's going on here. Okay, so this is kind of a cool trick. So this is This is the probability x greater than 4. Okay, cool. Now let's switch this around. Which larger, x greater than 2 or x bar greater than 2? Now we need to look on this side over here. Okay, so now the shaded regions we're coloring in are either going to be for, this is the shaded region for, this is the probability that x is greater than 2. Okay, and we can similarly do the probability that this is now the probability that this is the probability that x bar is greater than 2. Which one is now bigger? This one's going to be x bar now, because it's everything including the mean. So I get half, basically half the distribution has the mean, and all this distribution that's leading up to the mean. Only the tail is smaller, so I can do 1 minus the tail, and that gives me the opposite of here, right? So the answer in this case is now going to be the x bar question. Yeah.
So, question first, will we be, if you're like a question like this, will we be expected to justify like our answer?
Oh, on the final, I mean, it's possible I could say explain why as an essay question. Probably not going to ask something that tricky. But I could give you a multiple choice thing that's a small number of points that's asked this, right? If I'm probably not going to put a lot of these two. I think are fun. These are kind of trickier questions. I might put 1 or 2 things like this, but most of the questions won't be like this. Most of the questions will be just straightforward. Did you get the main idea? And maybe a couple that are a little bit more fun like this.
Okay. And then second, on B, did you possibly use the fact that the x's are independent to do that, or do they not?
Yeah. So this follows if I have IID random variables and I take their average, then the central limit theorem says these 2 things, A and B. And the third thing it says is the distribution of x bar looks kind of like a Gaussian. That's the kind of a vague statement, right? But the central limit theorem says A, B, and that it converges towards looking like a Gaussian. So this, at least this picture is somewhat justified. The red one, the black distribution, we don't quite know what it looks like. Yeah, so that's, and if they're IID random variables and I take the average of them, then A and B are following from the central limit theorem. And that's something I can expect you to know this on the final. Yeah. Okay. Great. So this was a fun one. Okay. Okay. So this is a concentration of measure with these inequalities question. And this one I think is a little bit trickier. I have a random variable that's in -1 and 2, and the expected value is 0. Okay, and I want to know the Markov inequality, the probability, an upper bound on the probability using Markov inequality. And the Markov inequality, yeah. So Markov says, let's assume I've got a random variable with x greater than 0, and I know the expected value is equal to some value mu that I know. Then I can say the probability that x is greater than alpha is less than the expected value of x, which I know, divided by alpha. Okay, I need to apply it here. Now, I told you use the Markov inequality, but I do not satisfy this property that x greater than 0. But I give you a hint, use a change of variables. So let's say z is going to be equal to x plus 1. So now I know the expected value of z is equal to the expected value of x plus 1 by the linearity of expectation. So this is going to be equal to 1. Okay. And now I can do the Markov inequality, the probability that x is greater than 1.5. This is equal to the probability that z is greater than 2.5, right? I add 1 to both sides of the inequality, and this is less or equal to the expected value of z divided by 2.5, and this is equal to 1 divided by 2.5. Okay, so you have to remember all the parts of the Markov inequality. You have to remember linearity of expectation to do this, but then it's kind of, then you plug in these inequalities, right? Once you can get it into this, something into this form, then you apply the Markov inequality. Does this make sense? I might ask you about these inequalities, but I'll probably give you simpler ones. There's also the Chebyshev and the Chernoff-Hofstadter. Those are a little bit harder to apply, you know, but hopefully you remember something about them. This is the kind of the Markov inequality, and usually, you know, ultimately it's simple, but you have to remember the right components here. Okay. Okay, on to linear algebra. Okay, we want to add a column to A so it's invertible, right? The key thing to remember here is what does invertible, what do I need for that? It needs to be full rank and square. Okay, so adding, it's right now it's got 4 rows and 3 columns, so I need to add a column for it to be square, right? And need to be full rank, so I can basically add anything that's not a linear combination of these rows, right? So if I can write it as a linear combination of these rows, I'm probably going to be in trouble. So I would probably do something like, well, 1, 1, 1, 72.364. That's probably pretty safe, right? It's some weird fraction. I'm probably not going to be able to get that, especially with the first one's 1. So so I can just say, okay, that's my column I'm adding. By telling you I can add a column and doing, you can kind of assume that the first 3 rows or columns are going to be linearly independent from each other already. And I just need to add another one, and that one seems pretty safe. Okay. Now I need to remove a row from A so that it is invertible. Okay. Yeah, so it turns out that none of these rows, I think these rows are all, well, I think any 3 of these rows are going to be linearly independent of each other. But when I originally wrote this question like 5 years ago, I had intended to put 4.5 here. In which case, if I put a 4.5 in that last spot, then the first and the third row, those are just a scale multiple of each other. So I'd want to remove one of those 2 rows. Okay, if that's the case, then I would say remove this row, and then they're going to be linearly independent. This is kind of hard to check by hand on a final exam, so I may not ask you something like this that you'd have to really check to make sure that was the case. But kind of, this is the main point I wanted to get, that if they were scale copies of each other, then you'd want to remove one of those 2 rows. That's something you should know, that if 2 rows are scale copies of each other, then they're not linear, then one is linearly dependent on the other. That should be something you should be able to pick up on the final. Okay, next is A transpose invertible. Okay, A transpose, right? So this is A transpose is going to be I'm going to have a 4x3 matrix times a 3x4 matrix. So this is going to be 4x4. Okay, so it's going to be a 4x4 matrix. What is the rank of this matrix going to be? Well, each A and A transpose are both rank 3. So this matrix is also going to be rank 3. So if it's rank 3, it's not full rank, so the answer here is no. How about A transpose A? This is going to be 3 by 4 times a 4 by 3, which is going to be a 3 by 3 matrix. And because A and A transpose, I kind of can imply from the question A, are going to be rank 3, then this is also going to be rank 3. And it's a square matrix and it has a full rank. So the answer is going to be yes here. Okay. Right. We typically have more rows than columns in the data with the way we talked about in this course. So A transpose A shows up more because it's invertible. Okay. So you should also kind of this, the A transpose A, this one should be something that is used a lot. So that makes sense. It's invertible. That's something you might be able to pick up. Yeah.
So if you did divide 4.5 instead of 3, then it would only be rank 2, right? So then.
Oh, it'd still be rank 3 because I'd have basically, if I have these 3 rows here, these are all linearly independent. They're still rank. I know it can't be more than rank 3 because it only has 3 columns. So the rank is at most the minimum of the number of rows and number of columns, right? So I still have 3 columns, so I know it's at most rank 3. Turns out these 3 rows in the blue box are going to be linearly independent of each other, so that it's going to be rank 3 by itself. And adding another row is not going to make the rank go down. Great, good. Okay, consider 2 vectors, u and v. Check if u or v is going to be a unit vector. Okay, first thing we can say is not v. A unit vector, remember, a unit vector is the norm of it equal to 1. And v, all of its entries are at least 1, and there are a whole bunch of them. So v is not a unit vector. You should be able to get that like off the bat just immediately. Its length is not 1. U might be a unit vector. All the entries are less than 1. Yeah, so that's some calculation. I will not ask you to do this much calculation on the final, but remember it's 0.5 squared plus 0.4 squared plus 0.4 squared plus 0.5 squared plus 0.1 squared plus 0.4 squared plus 0.1 squared is 1 equal to that. You know, remember when you square something less than 1, it goes down, right? So don't be, if I just added these terms up, they would clearly be bigger than 1. That you should be able to see quickly. But 0.5 is about squared is 0.25, right? So this is 0.25. I've got another one here. 0.4 squared is 0.16, 0.16, 0.16. And let's see, and this is 0.01, 0.01. I bet those add up to 1. Does that seem reasonable? 0.116 times 3 is going to be, what is that, like 48? 48 plus 2 is 50 plus 50. Yeah, that equals 1. That is a unit vector. Yes, u. Okay, so u is a unit vector. Okay, great. So the dot product u v. Okay, this dot product uv. This is going to be equal to -1 times 0.5 plus minus 2 times 0.4 plus 1 times 0.4. This is going to take me a while. All right, but I'm going to kind of add all these things up. I'm going to go out on a limb. I mean, do you want me to go and add them up, or I'm going to go on a limb and say that these are going to be equal to 0. If I add them all up, I'm going to have some negatives and some positive values, and I think they're going to cancel out. Okay, so you know, if they're equal to 0, does that make u and v orthogonal with each other? Yeah, if they're equal to 0, then yes, then these are orthogonal. If they're not equal to 0, exactly 0, then they're not going to be orthogonal with each other. Okay, and so vectors are orthogonal when their dot product is equal to 0. That's something you should know. Okay, as well. All right. Okay, and that corresponds. Remember, if v is u is a unit vector, and v is here, and the dot product measures, so they're orthogonal if this is a right vector, but if, say, I have remember, u is of length 1, and this is another vector p, then what the dot product measures, this is the length of p and u, is the length when I project a point p onto u, right? So if this is, if I project p onto u, then the length from the origin is the thing of the dot product, and that is exactly 0 with the orthogonal. V projected onto this there projects down to the origin, so I'm going to get a length 0. Okay, so that's why the dot product being 0 means that they're orthogonal with each other. And that's true even if u is not a unit vector, then it's scaling by u, and so it'd still be 0 even if it wasn't a unit vector. But okay, great. Okay, a long one here. Consider a matrix A. Each row represents a customer. There are n customers in the database. The first column is the age of the customer in years. The second is the number of days since the customer entered the database. The third is the total cost of all purchases ever by the customers in dollars. And the last column is the total profits in dollars generated by the customer. For each of the following operations, decide if it's reasonable or unreasonable. Okay. Run a simple linear regression on the first 3 columns to build a model for the 4th column. Yeah, we actually talked about an example like this with dongles. Yes, I think this one is reasonable. Okay, use k-means clustering to group the customers into 4 types using Euclidean distance between the rows as the distance. All right, is this one reasonable? I see some shaking heads no. Yeah, this one is not reasonable because I am using the Euclidean distance between dollars and years and days, right, as those quantities. And the Euclidean distance between, these, if I change the units of these things, then I'm going to be getting a different value. And so this is, I mean, it's probably not reasonable to do this. I'd want to think really carefully about how we define the distance, and this Euclidean distance does not seem like something that makes sense. Okay, so I would say this is unreasonable. How about doing PCA to find the best 2-dimensional subspace so we can draw the customers in the least error? Yeah, it's using the same problem in that it's implicitly using Euclidean distance. It's comparing these quantities which don't match with each other. So, this is it's not an uncommon thing that some people will advocate for you to do, but I'm going to tell you that's not reasonable to do. These quantities don't match. And again, changing the units is going to change the result. in an well, maybe a predictable way, but in a way that is not what your goal is to do here. Does not seem reasonable. Linear classification to build a model on the first three columns to predict if the customer will make a profit +1 or -1. Right? Does this seem reasonable? Yeah, I think I mostly intended this to be yes, especially if you use the perceptron. You know, I'm just finding a separator between some data sets. And if I stretch them, the same stretch separator will still be there if they're stretched. If I'm using a loss function, I'm kind of measuring, I will comment though, that if I'm using a loss function that's measuring this zi distance, remember this is equal to yi times f of xi, then I'm kind of measuring that distance, and if I'm having a cost based on that distance, so I'm using gradient descent formulation, this might be something that you could complain about, because then changes in units would change this distance. But I should be, if I build a perfect separator, it should be fine. But I kind of intended this to be yes. There are things you can do that are common beyond what we talked about in this class that would potentially cause problems. But in this setting, it's probably okay. Again, the supervised problems, these two are going to be, so supervised. And if my goal is just see whether I predict them correctly or not, then I can use that to kind of effectively like learn what the right distance and the right way to understand these things is. Whereas in the unsupervised ones, I don't have this ability, and I'm relying on the underlying distance, and then if I don't match the units, then I'm kind of in trouble. Or I could be in trouble, or something unintuitive could happen. Okay, great. This is a little bit harder to ask exactly like this on the final, because it's a little bit subjective, but good for in the review on the last day to drive that home. Okay. Now consider a data set xy, x and n by 3, decomposed into a test and train set. Assume that x train is not just a subset of x, but also pads, prepends all the ones. Okay, so I've built a model that includes something with all the ones, that with the constant factor in front, right? And then I have two remaining test points that are x1, y1, and x2, y2. And explain a mathematical expression to use the test state to estimate the generalization error. That is, if one new data point arrives x, how much squared error would I expect the model alpha to have compared to the unknown true value y? Okay, so I typically do this over a larger test set than 2 data points, but I can measure the error, so I can write the model down, right? So I can use the model alpha on, it's a dot product with x, but I want to prepend the 1 in front. Okay, alpha is, if I prepended the 1, it's going to be 4 dimensions. I should have said this is a 4 dimensions now. I don't know, maybe I meant to try and simplify this. But let's say it's alpha is 4 dimensions, x is 3 dimensions. The model, evaluating the model at point x1 is going to look like this. And then I want to say how much error do I have? I'd say typically the squared error is going to be y1 subtracting y1. It doesn't matter if I subtract the model from y1 or the y1 from the model and I square it. Okay, that's for one of them. And I want to do this, take the average of 2 of these. So again, I do alpha 1 x2 minus y2 squared, and I take the average. So I divide by 2. So usually I would divide by, if there are k things in the test set, I'd add them all up and I divide by k, but with 2 things, I can write it out like this. This will be the expected average squared error based on the test set. Okay? Makes sense? This is how I measure generalization error on the test set. Okay. Gradient descent. Consider a function f of x with gradient defined nabla f of x, x minus 1, comma, y, 2y plus x, starting at a value of x equals 1, y equals 2, and a learning rate of gamma equals 1. Execute one step of gradient descent. Okay, so now we want to, first thing I want to do is I want to evaluate the gradient at values x equals 1, y equals 2. And this is going to be equal to 1 minus 1, 2 times 2 plus 1, okay, which is going to be equal to 0 and 5. Okay, this is my gradient. And then gradient descent, I'm going to be at a value x equals 1, y equals 2. And I'm going to then subtract from it gamma times the gradient, right? And this is going to be my new, right? This is going to be my new value. This is one step of gradient descent. So I have 1, 2 minus 1 times this is 0, 5. Okay. So 1 minus, this equal 1 minus 0, comma, 2 minus 5. And this is equal to 1, negative 3. That'd be one update here. Okay. Gradient descent, again, it's this. This is really the key thing you need to remember, what the one step of gradient descent is going to be. Probably a few people will forget to use the minus sign and they'll add it instead of the minus sign. You know, that happens. But this is the key thing you have to remember how gradient descent works. Okay, and you plug in the numbers and yeah, that's it. Okay. Okay. Good. Okay, this is a more kind of fun question here. Consider running gradient descent with the fixed learning rate gamma. For each of the following, we plot the function value over 10 steps. The function is different each time, right? You know, each of the steps. Decide whether the learning rate each line is for a different function. Decide whether the learning rate is probably too high, too low, or so about right here. Okay. Let's look at F1 here. I'm going down my function value as I'm running gradient descent. It's 100, 99, 98, 97, down to 91. Does this seem like this is good? No, yeah. So it's kind of going down smaller, but it's going down by about the same every time. So I could probably, like, if it's going good, it should be kind of, it should be asymptoting. So I would probably say the learning rate is too low here. This would be too low, right? I could step it up a bit and make more progress here. Okay, let's say the second one now. 100, 50, 75, 60, 65, 45, 75, 110, 90, 85, right? Have up and down a little bit here. What's going on in this case? Yeah, this one's too high. Okay, good. 100, 80, 65, 50, 40, 35, 31, 29, 28, 27.5, 27.3. This one seems about right. This is like baby bears, kind of porridge. And then the last one, 100, 80, 60, 40, 20, 0, negative 20, negative 40, negative 60, negative 80, negative 100. So it's too low, right? Yeah, this is the tricky one. This one is also too low. I didn't say the function had to be always greater than 0, right? I'm going down. It's the difference between the values you really care about here. And the difference is staying the same, just like in A. So this one is also too low, even though I'm dropping below 0. Typically, in most data analysis, your cost function always stays above 0, but that does not need to be the case. You can always write the cost and subtract some big number from it, and then the values are less than 0. These are the function values, not the gradient. The gradient is basically constant. It's probably going to be about constant for this one, and A is going to be all over the place for B, and C, the gradient will be decreasing probably with the fixed learning rates. Okay, cool. All right, into the stuff on dimensionality reduction. Okay, consider a matrix A. It's an 8x4 matrix with squared singular values. Sigma 1 squared is 10, sigma 2 squared is 5, sigma 3 squared 2, sigma 4 squared 1. It's 8x4, so it only has 4 singular values. The singular values at most the rank, which is the the smallest of the 2 dimensions. Okay, so what is the rank of A? The rank of A is going to be 4, which is equal to the number of non-zero singular values. Right. So this intuition would be helpful for the earlier question on is it invertible sort of questions. Okay. What is A minus A2 the Frobenius norm squared, where A2 is the best rank 2 approximation of A? Okay, the Frobenius norm of A, the squared Frobenius norm is actually the sum of these squared singular values, right? So, but I've subtracted off basically the best rank 2 approximation uses the first 2 singular values. So what's left is the last 2 singular values. So this one is going to be sigma 3 squared plus sigma 4 squared equals 2 plus 1 equals 3. Okay? Okay, so the squared Frobenius norm is the sum of the squared singular values. That's kind of a cool trick, cool thing to know. Whereas the spectral norm, with the 2 norm of a matrix, is just going to be the largest singular value. So the 2 norm squared, the spectral norm squared, would be 10 for A. What is it going to be? A minus A2. Where I'm getting rid of the first 2, so I just have the third one left. The third one, yeah. So the answer here is just sigma 3 squared, which is just going to be equal to 2. Okay? And then I kind of answered these already. This guy is the sigma squared of all of A. This one is going to be 10, or spectral norm squared of all of A is 10, and the Frobenius norm squared, this is going to be 10 plus 5 plus 2 plus 1, which is 17. Okay? Okay, cool. Let V1, V2, V3, V4 be the right singular vectors of A. What is A times V2 squared? A times V2, that corresponds, these ones correspond with each other. Okay, and it's going to be, I'm projecting A onto the singular vector, of course, corresponding with the second singular value. This is going to be sigma 2 squared, which is equal to 5. Okay. What is V1 dot V3? 0. These are orthogonal with each other, right? All the singular vectors are orthogonal with each other. They'd form an orthogonal basis of the space that has these very nice properties. And then what is the norm of V1? It's going to be 1. Yep, these are all the singular vectors are going to be unit vectors. So their norm is equal to 1. Okay. Great. Then let A be the first row of A. A1, little a1 be the first row of A, write A1 and the basis defined by the right singular vectors of A. Okay, so I'm going to give a new basis, and this is kind of, so basically what I want to do is write A1 in the basis defined by these right singular vectors. It's still going to be a vector in R4, and it's going to be V1. Write this more clearly. V1 dot A1 is going to be the first coordinate. V2 dot A1 is going to be the second coordinate. V3 dot A1 is going to be the third coordinate, and V4 dot A1 is going to be the fourth coordinate. So this will be a point in R4. This will be in the basis here. So this is equivalent to V transpose times A1. So if I had just written this, that would also give me a vector that's going to be in V4. Okay, so the idea, and I have another page here, is that so kind of there's going to be an original basis. This is the original kind of X and Y coordinates, maybe X1 and X2 coordinates. And then I'm going to get these new orthogonal vectors, V1, V2. I can only draw two of them now, right? These are going to be orthogonal, and there's going to be some underlying data points, right? And we're going to kind of model this as centered. We're modeling, when we do the SVD, we model centered. If we don't model the data as being centered around the origin, we need to do PCA and center it first, okay? But I'm kind of modeling this data, and the singular value, this is going to be kind of correspond with sigma 1 and this sigma 2. It's kind of something like the standard deviation. It's the way to conceptually think about it. If the data is centered, it's kind of like, it's a lot like the standard deviation along the direction V1 and V2. And you see there's more spread along V1 and V2. And when I have a data point, actually, let's pick this guy as A1, call that guy A2 now. The new coordinate system is I'm taking a dot product. These are unit vectors. So I'm getting the coordinate in this direction. That's the first coordinate. This length is V1 dot A1. And then I'm also projecting onto here. And this length is V2 dot A1. That's what is measured, the length with the dot product onto the unit vectors V1 and V2. So it's the same point in the original XY. I haven't changed the geometry of the point. I'm just representing it by saying, well, I move this far. I'm moving kind of this far along this V1 direction and this far along this V2 direction. And they both tell me, you know, how I get to this point, A1. I could have instead used the original coordinates of A1, and I get it on the original basis, but I've changed the basis. Instead, from the black original basis, the way the coordinates are written, I'm getting a better one, V1, V2, which is still orthogonal, still unit vectors. I still can describe the points, but this one is aligned with the most variation in the data. And that's what the SVD is giving me with the right singular vectors. Okay. Cool. Right. This was, I think it's really a tricky point to conceptualize, but this is the key picture to keep in your mind. If you understand what's going on with this picture, you know, all the components of the, you know, V1 and V2 being orthogonal and unit vectors and describing a basis, this will really kind of make a lot of stuff clear, right? And the kind of the sigma 1, sigma 2 are the length associated with the full data set A kind of along these coordinates here. Okay. Great. Okay. The Voronoi diagram of points, clearly I like to ask questions like where you just draw something on paper quiz, but we clearly can't do that with a Canvas quiz, but it should be kind of the bisector. I could ask you, okay, is this the Voronoi diagram? Here, let me ask you, is this the Voronoi diagram of these points? No. Okay, there's some stuff missing. I need to have this part here, and maybe should be some change here, and at some point, I'm still going to kind of get this. Yeah, it's going to look something kind of like this. Okay, I've kind of drawn the bisector between any kind of points which are neighboring to each other, extending them until it's equidistant from about 3 points. For instance, this point, this intersection point here is kind of equidistant from these 3 points, and there's kind of a circle here. Whereas this one is equidistant from those 3 points. That's kind of what's going on. Okay, and this is kind of associated with clustering in the case that if there were some data points, all these data points in this FoDA diagram would be assigned onto this site 2 in the mapping described by these assignment-based clusterings. Right, so if these are the sites of assignment-based clustering, this describes the mapping of which points are mapped onto which site. Okay. Okay, what would you do if running Lloyd's algorithm for k-means clustering with k equals 2, and you reach this sort of scenario? Here, the black points are data points, the red stars are the sites where the algorithm terminates. The black, yeah, and the algorithm is terminated. Right, if I draw the Voronoi diagram here between the sites, okay, well, you can see the half of the black points above and below, they're actually copies of each other because of how I drew it, and it's intended that the mean of the points is exactly at the red star, and that's true here too, right? So I have the mean is here, and this stopped. Is this probably the right answer for the best 2 means clustering? No, it's not. I'd rather have kind of site 1 here and site 2 over here, right? So yeah, so Lloyd's algorithm doesn't always find the right answer. What's one strategy I could do if I get in a situation like this? Say, yep, the simplest thing is a random kind of restart, right? Where you randomly change where the initial sites are and you rerun the algorithm. You sometimes need to do this, okay? There are lots of these kind of layers and tricks you put on Lloyd's algorithm. One of the reasons we didn't kind of go and implement it, but it's built into most, data analysis libraries. Okay. Okay, great. Consider the loss function. Okay, this one's probably a bit trickier. The loss function, Li of Zi, or L of Zi, 1 minus Zi squared divided by 2, where for a data point x, y, and predicting function f, then we define the z function in this way, right? This is the standard way, yi times that for the function. And that says if the signs match, it gives a positive value. If the signs don't match, it's a negative value. Remember, yi is always -1 or +1. Then predict how this might work with the gradient descent algorithm for classification. Okay. When you get a function like this, I would say the right thing to do is on scratch paper or wherever is to draw a function. When you think about these loss functions, draw a function of z, right? This is the zi value. Okay, and then we want to try and draw, and remember, we would like it to have no penalty for zi values here, and then a penalty of 1, right, for this delta function, right? This is a penalty of 0, penalty of 1. We'd like this. So we have a penalty. I misclassified a point if the zi value is negative. I've classified it correctly positive. If it's positive, and this is my cost function, what is going on with with this function now? What does this look like? Well, let's say I have 1 minus zi. So if zi is equal to 1, this is an interesting point to consider, right? So if I say 1 here, then the function is going to be 0, right? Because I take that squared divided by 2. Okay, and then what happens as zi gets, say, is 1/2, right? If zi equals 0.5. Well, I do 1 minus 0.5 squared. So that's 0.25 divided by 2. Well, that's going to be 1.25. So at 0.5, I'm going to get something like here. Okay, and then let's put in 0. If I put zi is equal to 0, that's an interesting thing. Then I'm going to get 0 divided by 2. Oh, no, I'm going to 1 minus 0. So 1 divided by 2, I'm going to get 1/2. And let's put in at minus 1. So this is equal to 0.125. This is equal to 1/2. Minus 1. This is equal to, that's 1 minus negative 1 is 2 squared divided by 2. This is equal to 1. Right? So if I go out to minus 1, I'm going to get up to 1. So it's kind of going like this. And it's, so this should be a parabola. Right? So it's a parabola here. And this part looks okay. It's not always greater than delta. That's often was kind of a goal here. It can always greater than delta, but you know, it's a pretty good approximation of delta on this side, I guess. It's not bad. But what happens on the other side? Well, it's going to look the same way. It's a parabola here as well. Okay, so when we want to run gradient descent, there are a few things that we want. We want it to be so convex. Check. It's a convex function, right? It's a convex function. We want it to be differentiable, right? This is a differentiable function. It's a polynomial, right? It's differentiable. Okay. We want it to approximate delta. Does this approximate delta? It does on the left-hand side. It's not so bad over here. It's about as good as some of the other ones. But we get larger values of zi over here, this becomes a problem. As we get better, this direction corresponds with kind of, better classification. Okay, as we get points better and better classified, they're penalized. We don't want to penalize points for being better classifications. Okay, so it might tend to, so the answer to this is, well, gradient descent would run, we'd be able to implement it, that would be fine, but it might try and move points somewhat close to the margin, not penalize them for good classification is what would happen. And so that's why we typically don't use these sort of squared error loss functions here. We use something like a hinge loss or a kind of a logistic or a squared hinge loss instead of here, what we'd like to do is this would be okay if it went, like this instead, where it flattened out, but the issue kind of here is the error. Okay, so that's kind of a good demonstration of what you need to understand for these loss functions. Yeah.
Just so I can clarify, the higher, essentially the farther it gets off delta to the left-hand side, so the higher it spikes, means it's more affected by outliers.
Yeah, okay, yeah, that's another good point. These are kind of, so outliers get a large penalty. You'd rather do something like the hinge loss or the squared hinge loss, which kind of looks parabolic and is differentiable everywhere, but only has a linear growth as it goes up. That one's going to be more resilient to outliers. Yeah, this one will be also affected by outliers, even if they are hard to classify correctly. Okay, great, good point. Yeah, it's kind of yeah. Okay, last question on classification. This is a KNN, K nearest neighbor classifier, K equals 3. I think it's still a useful question, even though it's kind of not one of the core things we talked about here. Again, it's useful because I think it's useful to kind of how to think about these sort of problems. Your X is now going to be this one-dimensional data. So we're going to draw the plus points. Let's draw the plus points first here. Yeah, so okay, so we're going to start at 0 and this is going to be a plus, x equals 0, x equals 2, this will be a plus, x equals 4, x equals 8, this would be about here. This will be, what did I do here? These are pluses, this is a plus. And then we draw some minus points as well. So x equals 1, this is a minus point. X equals 5, this is 5, this is a minus point. No, that should be 6. Sorry, 6 should be a minus point, 7 should be a minus point, and 8 and 9 should be a minus point here, okay? And then I've asked you to do some queries at these points, 3, 9, and at -1. We're gonna do K&N classifier. And the key insight is often try and draw a picture of a mental model. But in this case, I'm going to find the 3 nearest neighbors. Let's do x equals 3. Done this, so hopefully it's unambiguous. X equals 3 nearest neighbors are these points. I have plus, plus, minus. I'm going to predict a plus. For -1, the 3 nearest points are going to be here. Again, a plus, and a minus. The prediction is going to be a plus. For 9, the 3 nearest points are 9, 7, and 8, including itself, right? And I'm going to have a minus, minus, and a plus. So the prediction is going to be a minus. I vote. Okay. So this is how you do a K&N classifier. So I could ask you a question similarly for like a linear classifier or something else, and to make a prediction. Okay, but again, if you have a picture, maybe we'll provide you a picture even. Yeah, but understand how to do these things. Okay, great. So we're almost out of time. We have 3 minutes left in this semester. Any last questions you have for me? Yep. Yeah, I have no idea. I have wondered that for a long time as well. That has been like that on my iPad for several years. If you look back at my earlier lectures on YouTube, I think it's also there. That is a really good question. Maybe I'll ask for a bonus question on the final. What date does it say on my iPad? But yeah, where is it? Can you see it on this screen? Okay, so only if you watched on Zoom would you be able to see that. So maybe not a fair question to ask for you in person, people. Yeah, if you find out the answer to that, I would like to know. Yeah, as soon as the time works when I'm not sharing the screen or something, but it's always that date and time. So maybe it's the end of the world. I don't know. So I hope not. Well, it doesn't say what year it is, so we'll be, All right. Well, on that positive note, thanks for coming this semester. It was a lot of fun. You were so great class. If you have any questions about next steps in data science or something, I'd be glad to share some thoughts on that. And good luck. Finish up your homework. The last homework due tomorrow at the end of the day.